Hey everybody, Dr. A here, and in this video we're going to be exploring another example of transverse shear stress. So let's go ahead and get started. In the given information, we're being asked to compute the maximum shear stress in the beam. So the beam we're given is what's called a compound beam, and we know that because we have a fixed connection at A, an internal hinge at B, and a roller at C. Now, even though the problem or the figure does not explicitly say there's an internal hinge at B, we know that there's one because we see we have two beam segments, beam AB and beam BC, and we see that they're connected together by a strap or some kind of bolted plate system, okay? And so you see a couple of bolts on each side that are holding these two beam segments together. Now, along the segment AB, we've got an applied 200 PLF, and at the midspan of BC, we have 500 pounds. We're also being told that the cross-section of this beam is a rectangle that has a 4-inch height and a 3-inch width. So let's go ahead and start tackling the solution. When we want the maximum shear stress in the beam, we know that that's going to be tau is equal to VQ over IT, and this is going to be at the neutral axis. So if you remember, maximum shear stress occurs at the neutral axis within the cross section. Now, for a rectangular section, we have a simplified formula that we can use, and in fact, we saw another example where we derived it. So I'm going to make a note here for a rectangular section, we can say tau max is equal to 1.5 V over A, okay? Now what's A? A is just the cross-section area, so in our case, it's 4 inches by 3 inches, so we can say that that is 12 square inches. So we can go ahead and check off A right here. So the work in this problem is really to do what? It's really just getting V. And in particular, what do we need? We actually need V max, okay? Because again, we're looking for the maximum shear stress. So we need a maximum of everything involved, okay? So how do we get V max? Well, really, this is just a shear diagram problem, okay? Really, it just goes back to basic statics. We need to draw the shear diagram of this beam, and we need to find where the shear force is a maximum, okay? And again, one more time, remember, for rectangular sections, when it's a single rectangle right here, the maximum shear stress, which will occur at the neutral axis, is just going to be simplified as 1.5 V over A. And that formula is derived originally from VQ over IT, which I have a separate video on where I do derive that, all right? So let's go ahead and draw the shear diagram for this beam. In order to draw the shear diagram, we first need to solve for external reactions, but before we do that, we need to disassemble at the internal hinge, all right? So let's go ahead and do that. Disassemble at internal hinge B, okay? And so when we do that, I can draw a new free body diagram that looks a lot like this. I've got the disassembled hinge at B, and I'm going to have some reactions and some applied forces. I've got that 500 pounds here, and I know I'm going to have a CY, and I'm going to have a BY, all right? Now, on the other side of BY, or on the other side of that internal hinge B, I've got the same BY, but notice it's going to be pointing in the opposite direction of the free body I'm starting with, okay? And then I've got a BX, which is going equal and opposite at the two sides of the internal hinge. And then, of course, I've got my uniform load here. That was 200 PLF. And then finally, I'm going to have my AY, I'm going to have an AX here, and I'm going to have a moment here. Now, all of these unknowns, I don't know yet, right? I don't know yet, but I can solve for them here in a minute. All right, so I've got a 20-foot length here, and I've got a 5-foot length and a 5-foot length, okay? And so I'm going to start my analysis with analyzing this right free body diagram, okay? I'm analyzing segment BC because I only have 3 unknowns. Notice that I cannot start with AB right now because I have too many unknowns. I've got the 3 unknowns at A, plus I've got some unknowns at B. So I'm going to make a note here just to refresh our memory. We're going to say begin analysis with BC since there are fewer unknowns, okay? And then I'm going to say by symmetry, clearly BY equals CY equals 250 pounds reacting upwards, okay? And then also BX is going to be equal to 0 because, again, just looking at this free body, you have nothing applied in the X direction, all right? And so now I'm going to move over to the left free body diagram. And in this left free body diagram, of course, BY is 250 pounds, but it is, in fact, pointing down in the left free body because in the right free body, it was pointing up by this calculation here. And so looking at this left free body, I can say, I'm going to say free body diagram of AB now. And I'm going to say AY equals, and we're going to pull out our calculators and we can get AY pretty straightforward, 200 PLF times 20 pounds, and you add to that 200, times 20 feet, add to that the 250 pounds, and so you get 4,250 pounds reacting upwards, okay? And then we're going to be able to say the moment reaction at A is going to be 200 PLF times 20 feet times 10 feet, and add to that 250 pounds times 20 feet. And so for MA, we should get 45,000 pound feet, and that is in fact going to be reacting counterclockwise. And then of course AX is 0. Now I went kind of quickly through this because this process is really just statics. This is basic beam analysis of a compound beam that you should have gotten in a statics course, not really a mech of materials course, which is why I kind of skipped some simple steps here. All right, so now we're ready to draw our shear force diagram. All right, so I'm going to go ahead and sketch that out. I've got my axes here, V, and I'm going to go ahead and use kips instead of pounds, just because I've got lots of thousands of pounds here. And then I've got X in feet here. Okay, so in our shear diagram, the first thing we're going to encounter is AY. So that's going to be 4.25 kips going up. So I'm going to say that's about right here. 4.25 kips going up. And now the next thing we encounter is this uniformly distributed load. So we're going to say 4.25 minus 0.2 times 20 feet. And so that's going to put me down to a positive 0.25. So I'm going to say that that's about right there. 0.25 kips. Now that's going to be connected by a straight line segment. Okay, so let me draw that a little bit better for us. So that's a linear segment there, okay? And then, you know, we've reassembled this thing, right? It's completely reassembled and it looks like this again. So we're going to stay constant for the next 5 feet until we get to 500 pounds, all right, or 0.5 kips. So that's going to keep us constant. And then we're going to hit the 0.5 kips, so that's, or 500 pounds. So that's going to push us down to negative 0.25. and then we're going to stay constant for another 5 feet and then go back up to 0. So this is our shear diagram, okay? So what is the absolute maximum shear force? Well, it's this 4.25 kips. So we can make a note. We could say Vmax is 4.25 kips, okay? And so what's our final answer? Well, tau is going to be equal to 1.5 times 4.25 kips divided by 12 square inches. That was our area. And we punch that through, and let's see what we get. 1.5 times 4.25 over 12. And so I get 0.531 KSI, or you could just as easily write 531 PSI. Either one is the correct answer. So that concludes our example. Notice we did not need to draw the moment diagram because we just needed to find the maximum shear. So no need for the moment diagram in this problem. We could have drawn it if we wanted to, but no need for it. So hopefully you found this example helpful. If so, please hit like and subscribe and be on the lookout for other videos like this. Thanks for watching.